All right, what if I told you there's a single physics question out there that has been sent to literally thousands of the brightest minds on the planet, and it has left every single one of them stumped? Well, today we're going to break down that exact question.
And no, that is not a typo. We're talking about over 5,000 professors, experts from top universities all over the world. They've all seen this problem, and so far, not a single one has come up with a concrete, definitive solution. This is way beyond just some tricky homework problem. This is a real-deal scientific puzzle.
This is how the letter sent to all those experts begins. Assistance is kindly requested in solving a challenging problem in physics. You can just feel the tone, right? It's formal, it's serious. This isn't some casual brain teaser. It's a formal call to arms to solve a problem that seems to fly in the face of a fundamental law of our universe.
Okay, so to really get why this puzzle is such a head-scratcher, first we need to get our heads around the rule it seems to be breaking. And listen, this isn't just any rule. We're talking about the second law of thermodynamics. This thing is considered one of the most solid, totally exception-free laws in all of science. It's a big one.
So, what does this law actually say? Well, in pretty simple terms, it means that for any closed-off system, one that isn't interacting with anything else, the total amount of disorder, or what scientists call entropy, can never, ever go down. It can stay the same, sure. It can go up, but it can't decrease. It's kind of like the universe is on a one-way street, always heading towards more randomness.
Let's dig into that just a little bit more. So, entropy is basically just a measure of that disorder. We call it delta S. And, calculating the change in entropy is actually surprisingly simple. It's just the amount of heat energy you move around, we'll call that Q, divided by the temperature, which we'll call T.
Now, this is the really crucial part, because temperature, T, is in the denominator of that little formula. The exact same amount of energy has a totally different impact depending on whether it's hot or cold. So think about it. If you add some energy to an already hot area, you're dividing by a big number, so the change in entropy is pretty small. But if you take that same amount of energy away from a cold area, you're dividing by a small number, and the change in entropy is massive.
And this is exactly why heat always flows from hot to cold. It's not magic, it's just math. For the total entropy of the universe to always go up, which is what the second law demands, energy has to flow this way. The little bit of entropy you lose in the hot place is completely swamped by the huge amount of entropy you gain in the cold place. The books balance and total entropy goes up. It's just the natural order of things. Or at least, that's what we've always thought.
Okay, so with all that in mind, let's get to the experiment that just throws a giant wrench into the whole system. Now, it's a thought experiment, but it is based on some very, very real physics. They call it the gravitational battery.
And look, this isn't just some made-up sci-fi concept. It's actually grounded in a discovery from way back in 1910. A physicist named R.C. Tolman proved that if you take a tube of electrolyte and accelerate it, a voltage just appears. And since gravity is just a constant form of acceleration, this whole thought experiment is just applying Tolman's real-world findings to a system that's sitting still right here on Earth.
Okay, so here's how the experiment is set up. Step 1, you take two different electrolyte solutions and put them side by side. Step 2, thanks to Earth's gravity, a small but stable voltage just naturally forms between them. Now, you take this entire setup, this is our battery, and you place it inside a cold region. Then, you run some wires from it to a simple resistor, but the resistor is sitting in a totally separate, hot region. The circuit is now complete, and just like that, a steady electric current starts to flow.
And here is the jaw-dropping result. The electric current starts carrying energy from the battery in the cold region to the resistor in the hot region, which makes the hot resistor get even hotter. Let me say that again because it's the whole point. Energy is flowing on its own from a cold place to a hot place.
Yeah, I think you can see where this is going, right? We now have a direct conflict, a full-blown paradox between what we see in this experiment and that unbreakable cosmic law we just talked about.
Wait a second, didn't we just establish that energy is supposed to flow from hot to cold so that total entropy can increase? That's the rule! But this setup, it's doing the exact opposite. So what on earth does that do to our entropy calculation?
Let's just follow the math. It's simple. In the cold region, with the battery, energy is leaving, so that's a negative Q. And since it's at a low temperature, that creates a big negative change in entropy. Meanwhile, over in the hot region with the resistor, that same amount of energy is arriving, so that's a positive Q. But because it's at a high temperature, it only creates a small positive change in entropy. So what happens when you add them up? The big negative number is way bigger than the small positive number. The total entropy of the system seems to go down.
And this is it. This is the core of the puzzle that was sent to over 5,000 professors. If the second law is absolute, if total entropy must always increase, but our simple calculation here shows a net decrease, then something has to be missing from our equation. Where did the missing entropy go? How do we balance the universe's books?
Look, this isn't just some old historical curiosity. This is a live, ongoing scientific debate. And now that you understand the law, the experiment, and the paradox, you're pretty much in the same boat as all those experts, ready to think this through.
So, what are the possible explanations? Well, the debate is all over the place. Some people say, hey, maybe the system just isn't at its final stable equilibrium yet. Others think there must be some hidden chemical reactions we're not accounting for. But here's the kicker. The person who proposed this problem says they've actually measured power coming out of a similar setup for nearly 2 years straight. That's way too long for it to be a temporary thing. And that leads to a much crazier idea. What if this is a real, true exception to the second law? Maybe a tiny crack in the foundation of physics that only shows up when you mix gravity and electricity.
And that brings us right back to where we started. All of these ideas have been kicked around and debated by those 5,000+ experts, and yet not a single one can definitively explain where that missing entropy is coming from. The question is still completely open. So now it's your turn. We've laid out the unbreakable law, we've walked through the experiment, and we've stared right at the paradox. You now have the exact same information as thousands of top physicists. So, what do you think is going on here? What's the piece of the puzzle that everyone seems to be missing?